Hello everyone, this is Vipin here. Welcome back to my channel. So in this video, I'm going to solve the question number 40 from the GATE Aerospace 2022. So let us quickly go through the problem. So consider a conventional subsonic fixed wing airplane is the Ostwald efficiency factor and aspect ratio is AR. So corresponding to the minimum CD upon CL power 3 by 2, which of the following term is true? Okay, so the condition is given the minimum CL by CD upon this. Okay, so minimum means the minimum value is there. That means to find out the minimum and maximum, what we take basically, we take the slope of the given parameter as 0. So this is basically with respect to the CL. So what we will be doing, we will be taking its first derivative with respect to CL equal to 0. CD power CL 3 by 2, which is equal to 0. Okay, so quickly let us just solve it. So CL power 3 by 2 square, and here it is CL 3 by 2 into the derivative of d upon dCl of CD minus CD into d upon dCl of CL power 3 by 2, which is equal to 0. Okay, so CL power 3 by 2 on this side, and if we expand this as CD naught plus KCL square, so you will see that CD naught is constant, so that term becomes 0, but this becomes 2KCL. Okay, on the other hand, this is CD here, and the derivative of this is 3 by 2 into CL 3 by 2 minus 1. So 3 by 2 minus 1 is 1 by 2. Okay, so this is what we are having here. So from here we can write this in this way, and when we just rewrite this, so CL power 3 by 2 and CL power 1, so 3 by 2 plus 1 is 5 by 2. So CL power 5 by 2 into 2K is equal to CD 3 by 2 CL power 1 by 2. So if I take this 1 by 2 on this side, so 1 by 2 on this side from here, so it will become 5 by 2 minus 1 by 2 is how much? So that is CL square. Okay, so from here I can rewrite this as CD upon CL square is equal to 2 to the 4 K upon 3, and K is what? 1 upon pi EAR. So 4 by 3 pi EAR. So if we look at the options, this is the correct answer. Okay, so this is basically for 2 marks. So you can see that if you have marked this as the correct answer, then your 2 marks got saved. Okay, apart from this, we look at the question number 32, that is also from flight mechanics. So an unpowered glider is flying at glide angle of 10 degrees. So glide angle is given as 10 degrees, and it lift to drag ratio is asked. So we know that tan gamma is d upon L, or 1 upon L by d. Okay, so tan gamma means tan of 10. Okay, so that is 1 upon L by d, or simply L by d is 1 upon 10 of 10. Okay, so 1 upon 10 of 10 is 0.1753, something like that. So if you solve it, so you'll be getting your answer at 5.67. So 5.67 is the correct answer for lift to drag ratio. Okay, so this is one question. Apart from that, if so, this is one more. So question number 19 basically. So regarding the horizontal tail of a conventional airplane, which of one of the following statement is true? The first option is it contributes to Cm alpha less than 0. So that is true. Okay, so that is true means first option is true. So that is our answer. So second option is Cm alpha is equal to 0. That is basically the answer for neutral stability. Okay, now Tail is always stable, that we know. So the stability statement is this Cm alpha, which is the pitch stiffness, so that must be less than 0, or the slope of Cm versus alpha curve is 0. So this is CmCg versus alpha. So that is sorry, that is negative. So if that is negative, that means the airplane is stable. If this is positive, it is unstable. If Cm naught, which is this value, if that is positive, Cm naught is positive and slope is also positive. So you can see that if you extend this on this side, so its alpha trim also is negative, means it is not good for handling as well as not good for the stability. So all of these three options are incorrect and this is the correct option. The service ceiling of an airplane is the altitude. So we know that the answer for this is 100 feet per minute. So without thinking too much, we can answer it. Okay, let us take few problems from mathematics as well. So the equation of a straight line representing the tangent to the curve y is equal to x square at given point. So basically we know that the equation of a straight line which is tangent to a curve is given by this equation: y minus y1 is equal to m x minus x1. Okay, where m is the slope. So y1 and x1 is 1 and 1. So y minus 1 m x minus 1. So if you look at the options, so you even don't need to find this, and the option should be this one. Okay, this is the correct one. But let's say if you want to find out this also, so y is equal to x square, and what is slope? Dy by dx. So that is 2x, and the value of x is given 1. So 2 into 1. So it is y minus 1 is equal to 2x minus 1. So it is very simple question. Okay, so you can easily answer this without thinking too much. Now, next is, let us see this also. Let us see that the vectors I, j and k be the unit vectors in x, y and z directions, x direction, y direction and z direction. Okay, if the vector I plus j is rotated, this vector is given I plus j is rotated about positive k will be the vector for this. So it is basically rotating about this axis. Okay, about positive k. So first we need to know that equation of vector is I plus j, when the coefficient of these two is this. So the length of this is going to be, since the coefficient 1i plus 1j, so it is going to be 1 square plus 1 square. So that is under root 2. Okay, and angle of that is tan inverse uh, b upon a. If this is ai plus bj, so b upon a. So b is also 1, a is also 1, so tan inverse 1, which is 45 degree, means this vector is basically at 45 degree initially. Okay, I plus j. So it is at 45 degree, and if it is rotated by an angle of 135, means from here if it is rotated at by an angle of 135, so 135 will be coming on this one, on the horizontal x-axis in the negative direction. Okay, and what was the length of the vectors, this I plus j? So the length of that is under root 2. Okay, under root 2 here, and since it is falling on x-axis, so under root 2i. If it would be falling on this, it would be under root 2j. If it is falling somewhere here, then accordingly I plus j both will be there, but here it is under root 2 into I, and direction of that is minus, so answer is D. Okay, next, this is the question from the aptitude. You can see that the answer of this is 1. Okay, I'm not going to solve that. So this is the differential equation. This is the ordinary differential equation which is given, and the boundary conditions are also given. So we will solve this also as our last question of this video. Remaining problems we will be posting in the next part of this solution basically. So here you can see that the equation is given d square y upon dx square minus 2 dy by dx plus y. Okay, so if we take the operator d here, so I can write d square minus 2d plus 1 is equal to 0. Okay, and this is basically d minus 1 whole square, which is equal to 0. So from here d is equal to 1 and 1. So both root are same. So I can say that y is equal to c1 plus c2 x e power x. Okay, so this is the equation of y of this. Okay, so this is the solution of this particular differential equation. Now apply the boundary conditions. Y is equal to 0 and dy by dx is equal to 1 and x is equal to 0. So put x is equal to 0 in this. Okay, so when I put x is equal to 0 in this, so what I get, I will be getting y is equal to 0, c1 as it is, this is 0, e power 0, so e power 0 is 1. So from here c1 is 0. Second is dy by dx. So take the first derivative of this, which is dy by dx. So if I take that, so c1 into e power x. So c1 is constant and derivative of e power x is x e power x. Okay, x e power x. Now derivative of this. So derivative of second one is c into x e power x. So c2 is as it is, x into x e power x here plus e power x into 1. Okay, so we can write that this is dy by dx. So c1 x e power x plus c2 x square e power x plus e power x. Okay, so in this, if I put this equal to 1, according to this particular boundary condition, for the value of x as 1, x as 0, dy by dx is 1. Okay, so if I put these boundary conditions here, so I'll be getting 1 on this side, this x becomes 0, so this term is 0, this x becomes 0, this term is also 0. So from here you will see that c2 0 plus e power 0. So c2 is 1 from here. Okay, so c1 is 0, c2 is 1. So the equation of this line is y is equal to, this is 0, this is 1. So y is equal to y is equal to x into e power x. So this is the equation, the final equation by after applying the boundary conditions. And what we have to find out is the value of y at x is equal to power 1 by 2. Now in this equation, y is equal to x e power x. If I put 1 by 2 instead of this, so you will see that under root e by 2 is the answer, which is the option C. Okay, so this is question 37 of this. Now apart from that, if we see other questions, let's say I'm taking the question number 39 as the last question of this video. Remaining questions we will be solving in the next. So this we have already solved. Let me just give the solution for you guys also. So this problem is basically related to the similarity, flow similarity. Cylindrical object is given. So let us write quickly the data. So D1 is given 900 and U1 is 60 meter per second. Okay. And if its drag is estimated on a geometrically half scaled model, means second which we are going to test is basically D1 by 2. So it is 450 mm. Okay, 900 mm. So 0.9 meter, 0.45 meter. Okay, whereas U2 is not there. So U2 we have to find out. Uh, so its drag is this, but what else is given from here? So the mu1 is given and mu2 is given. So mu1 is basically for the air, which is 1.86 10 raised to power minus 5 Pascal second, and mu2 is 1.01 into 10 raised to power minus 3 Pascal second. Okay, respectively. So drag measured from the model means the model which is being tested underwater. Okay, so what we have to do here, we have to apply two things. First is the Reynolds number for let's say for air must be equal to Reynolds number for water. Okay, we have the value, so from here we'll be getting the value of velocity. So rho 1 u1 into d1 upon mu 1, rho 2 u2 d2 upon mu 2. Okay, so if we solve it and put, so you will be getting the value of u2. So what is the value of u2 from here? So u2, which is the velocity of the flowing water, so u2 you will be getting around 7.819 meter per second. Okay, so here you will be putting the values of velocity, density of the air, velocity of the air, diameter, this one in meters, viscosity, this one. Similarly for this also, these values you will be putting, and after that when you solve in calculator you will be getting u2 as this. Now we know that for the dynamic similarity their coefficient, so coefficient of drag in air must be equal to coefficient of drag in water. And what is drag? So that is drag force divided by q infinity into s. For air is equal to drag upon q infinity into s for water. Okay, so s is basically what? So s, let us just write the quickly. So this one which is inside the water is measured value, that is given, so that is 2280. Okay, so from here if I say that d from here is equal to 2280 upon q infinity into s for water and q infinity into s for air. Okay, so 2280 divided by half. Water density is 1000 into rho v square. So half into rho into v square. So velocity is 7.819 square. So that is the dynamic pressure. This one multiplied with pi by 4 of the diameter. So diameter for the water model is 0.45 square. Similarly here 1 by 2 into 1.2 into v square is 60 into pi by 4 into 0.9 square. So when you cancel out the terms and when you solve it, so you will be getting your answer, and the correct answer for the drag force is this. Okay, so this is the correct answer. So you can cross check the calculation and let me know whether you are getting the correct same answer or not. Okay, so with this I'll stop this video here and we'll continue with the second part of this with the few more solutions from this question paper. Thank you very much. Take care.